So what was found when these things were being researched? I'm not going to get into why this is true, but what was discovered when this was all being researched by physicists back in the 16, 17, 1800s. They found that the force between two fixed electric charges is given by what we call Coulomb's law. And Coulomb found that, like for gravity, electricity has what we called an inverse square law. So I want to remind you what the formula for gravity looked like. We discovered that Fg was equal to G, universal gravitational constant, times the mass of one object times the mass of another object divided by the distance between them. What Coulomb discovered is that electricity has static electricity has the same kind of force law, where the electric force, instead of the force of gravity, you can call it force electric, is equal to the two charges, so Q and Q, or you can call them Q1 and Q2, I'll use uppercase and lowercase, divided by the distance between them. And like gravity had this universal gravitational constant that was calculated, the electric force has this universal electric constant. It's which we give the letter K. The universal constants, or this particular universal constant K, has a value of 9 times 10 to the 9, and it has units Newton meters squared per Coulomb squared. One important thing to note is that we do not include positive or negative in the equation. We use positive, negative to determine direction. But otherwise, we leave them out of the equation. So let's do a couple examples. To find the direction of the force, we use the ideas from science. Again, it's not in Science 10 anymore. It's from science in middle school, I believe, where you have, if you have a positive and a negative, unlike charges are going to attract each other. So the force on these two objects is going to be in. And these two objects here, the force is going to repel. So the force on this guy is going to be up, and the force on this guy is going to be down. Because like charges are going to repel each other. We can actually figure out what these are. Let's say that these are electrons. This guy here is a proton. This guy here is an electron, and we want to figure out what the forces of repulsion and attraction are in each one of these cases. And so the only difference here is gravity was only an attraction force. The force of electricity now can be a repulsive force as well. Gravity will never be a repulsive force. So we can work out the calculation here for the electrons. Let's say that these two electrons are 1 millimeter apart. 1 millimeter, and that's going to equal 0.001 meters. Let's say the same thing is true for these guys here. Let's do the calculation. We know that these two are going to repel each other. So that's all we need the positive and negative for when we're doing these force calculations. So we can just use F equals K. I'll go Q1, Q2 this time. I don't know, you can write it either way. Over R squared. And so this is going to equal 9 times 10 to the 9 times, now these are electrons, so this is going to be 1.6 times 10 to the negative 19. On both of them, 1.6 times 10 to the negative 19. Because these are electrons, that's the elementary charge on a single electron, divided by the distance between them, 0.001 meters squared. And what you're going to find here is that the force between these two is 2.3 times 10 to the negative 22 newtons, which sounds very, very small. But these objects are also very, very small. And so if we remember for this, here, I'll just put a little box over here. because we're still dealing with this set over here. If we remember that the mass on a neutron, or electron rather, mass of an electron, if we look back, we'll see that the mass of an electron is very, very small, 9.11 times 10 to the negative 31 kilograms. Oh, sorry. And so if we actually want to see what kind of acceleration this force causes, we can just plug that into the F equals ma equation, where your force is 2.3 times 10 to the negative 22, and that's going to equal 9.11 times 10 to the negative 31a. You divide both sides by this number, 9.11 times 10 to the negative 31. You're actually going to find that the acceleration caused by the force of repulsion here is massive. It's 252,469,813 meters per second squared. The acceleration caused by two electrons repelling each other 1 millimeter apart is monstrous because those objects themselves are so small, which is pretty cool. We can see here that the electron and the proton in this case are going to have the exact same force because they have the same set of charges, except in this case it's going to be attractive. So these two are going to attract each other. Now the force on each of these is going to be equal. It's going to be 2.3 times 10 to the negative 22. What's going to change here though is their accelerations will change. The acceleration on the electron pulling it in is going to be the same here, because that's the mass of an electron. But the proton is going to be accelerating this way much slower because the proton is much, much heavier than the electron is. And if you wanted to take a look at what that force could be, the acceleration could be, you can do that calculation yourself. So let's move on here to example 2. If I have this particular setup, there's 4 charges placed here. I've got a positive Q charge, 2 negative Q charges, and a positive 2 Q charge here. All I want to find is the direction of electrical force on the positive charge. How do we do that? Well, what we have to do here is we have to look at what we've got going on at each piece. If this guy's positive and these two are negative, what I'm going to have here is I'm going to have a force straight down, and I'm going to have a force this way, and these two forces are going to be equal, pulling this way, because these two charges are equal. This force here, though, is positive, and this guy here is positive. So these two are going to repel each other. So I'm going to have a repulsive force going up that way. What we've got to do here is to find my net force. If I wanted to find my net force, we have to add these vectors together like we did before. We've added force vectors together. Nothing has changed. So either we use vector addition. We draw this thing, use sine and cosine law, all that stuff, where vectors are added tip to tail. Or we use components. And we add those together instead. If we had components, we would say, okay, well, I've got an fx and an fy here. These two, part of this fx would cancel out with that fy, and part of this fy would cancel out with that value of f. We don't know what the distances are. We don't know how big. Oh, we do know how big the q's are. But we don't know the distances, and so we can't actually find them directly, but that's how we would set up components. So let's do an example like that. So to solve these kinds of force problems, what we want to do is we want to express the charges in coulombs. We want to substitute the charges and the distance inside that equation, just like we did for gravity. Don't use positive and negatives. We're just going to use those to give us the direction. So don't actually put them into the force equation. So let's just jump down here and just do this example. We want to find the force on the electron in a hydrogen ion. So helium. This is a helium ion. Helium is a noble gas. They are hard to ionize, but you can ionize them. So we've taken one of the electrons away, and so now we've got He+1. So let's take a look at what we've got going on here. The nucleus is now going to be positive because it's got that 2 protons there. There's going to be a force of attraction inwards on that electron. So let's figure out what this is. This thing, the nucleus here, has two elementary charges, 1.6 times 10 to the negative 19. And so this nucleus has a total charge on it of 3.2 times 10 to the negative 19 coulombs. And so that's the charge we have to use there. So I've got F equals KQQ over R squared. K is 9 times 10 to the 9. That's a C, just so we're clear. These are brackets. The charge on the nucleus goes here, 3.2 times 10 to the negative 19. The charge on the electron is 1.6 times 10 to the negative 19. And the radius of the atom we're given is 2 times 10 to the negative 11 meters. So this is going to be 2 times 10 to the negative 11 squared. If you run that calculation, what you're going to find here is that the force of attraction is equal to 1.15 times 10 to the negative 6 neutrons, which again doesn't sound very big when we've been dealing with sleds and things rolling down hills and friction. We have large forces, but what you've got to remember is that electrons are incredibly small, so this force compared to that mass is huge. Let's do another one. See, we got that, and the calculation is done for us on the next page. That force was 1.15 times 10 to the negative 6 newtons. The mass of the electron is 9.11 times 10 to the negative 31 kilograms, which gives us a force, an acceleration towards the nucleus of 1.26 times 10 to the 24 meters per second squares. This is a huge inwards acceleration, which is why it's so hard to ionize helium beyond He+. Let's do another one. We want to find the electric force and the direction on the 1 microcoulomb charge below. So this is the microcoulomb charge. Let's color it there in green. And let's see what we've got here. This guy's got plus 1 microcoulomb. There's a negative 1 microcoulomb and a negative 2 microcoulomb. This one's 10 centimeters away. This one's 20 centimeters away. This type of question is exactly the same as the gravity questions we were looking at. The only thing we have to be careful with is we've got to make sure we know what direction the forces are actually going in, because now they're not just attractive, they can also be repulsive. So we want to find the net electric force and direction on the 1 microcoulomb. This is positive, this is negative, so there's going to be a force this way, a force of attraction, and we say that this is the force. I'm going to label these as 1, 2, and 3. This is the force on object 2 from object 3. And then we've got this guy going this way. There's going to be a force on 2 from 1. And now we can run both sets of calculations now that we know what direction these things are in. So the force of, the force from, on 2, from 1 is going to equal K Q1 Q2 over R squared. That's going to be 9 times 10 to the 9, 1 times 10 to the negative 6, 1 times 10 to the negative 6 over, and they're 20 centimeters apart, so that's 0.2 meters squared. We find that the force on 2 from 1 is 0.225 newtons, and it has a direction. It is to the left. So now we can do the force on 2 from 3. So I've got K, I'll have Q2, Q3 over R squared equals 9 times 10 to the 9, 1 times 10 to the negative 6. This is 2 times 10 to the negative 6 over 0.10 squared. And what we see here is if you do this calculation, we have a force here of 1.8 newtons, and this one is to the right. So if I wanted to figure out what the net force was, I just add these two together. I'm just going to relabel this F of 2 on 3, or F of 2 from 3. And we get that F net is equal to, I guess we can say that this direction we call positive, and so we're going to get 1.8 minus 0.225 equals 1.575 newtons to the right. And that is the net force. It's exactly the same kind of thing we've looked at before. The only difference here now is the calculations. The formula we're using is a little bit different because we're using slightly different concepts. But the formula actually looks very similar to gravity, and so this should be pretty easy. I'm going to skip ahead to page 359 to example 5 here. And we're going to take a look at this guy, and this will be the last one for this particular lesson. We want to find the electric force and direction on this electron from these two charged objects. So we can see here, if this is an electron, this guy has a charge. It's negative 1.6 times 10 to the negative 19. So this negative charge and this negative charge are going to repel each other. So if I'm going to call this object 1, and I'm going to call this object 2. So this one, these two are going to repel each other, so the electron is going to experience a force this way. I'm just going to call this guy F2. This is positive, that's negative, so there's going to be an attractive force down. I'll call that F1. So now we can find F1 and F2. F1 equals K, Q, Q. Again, it doesn't matter how you label the Q's, Q1 and Q2, or Q and Q, as long as you differentiate between the two and remember how to plug them in. So we're going to get 9 times 10 to the 9. The electron is 1.6 times 10 to the negative 19. Remember, we don't use the negatives in the formula. We use the negatives to give us the direction, and then we're done with them. And then the other charge is 2 times 10 to the negative 6. And the distance between them is 2 micrometers. 2 times 10 to the negative 6, and we want to make sure we remember to square that. It's something I always forget to do. And we find if you do this calculation that the force, actually that's F2. Sorry, I mislabeled them. The force from 2 is going to be 0.00072 newtons. We can do the same thing for force 1. F1 equals K, Q, Q over R squared equals 9 times 10 to the 9. Now we've got the 1.6 times 10 to the negative 19 charge on the electron. This guy has 1 times 10 to the negative 6 coulombs, 1 microcoulomb. And these guys are also 2 micrometers apart, so that's going to be 2 times 10 to the negative 6. We want to square that. We find that force 1 is equal to 0.00036 newtons, which we could have expected because the distances are exactly the same, the electrons are the same, this constant is the same, but this charge here is twice as big as this charge there. And now we want to figure out what the net electric force is. But we can see we've got these guys going off in different directions, so we actually have to draw these things out. So I've got F2 going this way. I've got F1 going this way. This is 0.00072 newtons, and this guy is 0.00036 newtons. So my net force, again, I'm adding these together tip to tail. I took the force 1, and I put it to the tip of force 2. The net force goes from the tail to the tip of the second one, and this is going to be my direction in there. So my F net is going to equal the square root of, these guys are perpendicular to each other, one's to the left and one's down, the square root of 0.00072 squared plus 0.00036 squared. And that's going to equal 0.00081 newtons. And for direction, we can see that that's going to be the tan inverse opposite 0.00036 over adjacent 0.00072. And that's going to give us an angle of 26.6 degrees, if I've done my calculations properly. And that would be, we would say that this is 26.6 degrees. Well, for lack of a better term, it's below left. We've got left and down, and so this guy's gonna go this way, below left. There's no north, south, east, west going on here. We have no idea what's up or what's down. So this would be my final answer here. And that's it for this lesson. Take a look at the questions I'm going to assign here on the next page. I want you guys to take a look at 1A, C, and D. 7, 9,